Hello student, very good morning to all of you. Do you remember what were we discussing yesterday? I think we were discussing about the general mechanism of aromatic substitution reaction, and while discussing the aromatic electrophilic substitution reaction, we found that the mechanism is follows two steps, or mechanism involve two steps. First step, attack of the electrophile to the aromatic nucleus, first form the pi complex. After that it is converted into formation of sigma complex, and finally in the second step there is a aromatization and resulting compound obtained is a aromatic once again. So that type of the general mechanism we have discussed about aromatic electrophilic substitution reaction. So what we are going to discuss today, let us see here effect of substituent groups, orientation and the reactivity. Whatever reaction we have seen so far about the aromatic compound, we know that the speciality or the special feature of the aromatic compound or the important characteristic of aromatic compound, any according to as a Huckel's rule, any cyclic, planar, fully conjugated containing 4n plus 2 pi electron shows aromatic behavior. So now whatever reaction we have seen about that aromatic compound, the some of the few reaction, and they are frequently you are familiar with those reaction. Number 1, nitration. Number 2, sulfonation. Number 3, halogenation. Number 5, Friedel-Crafts alkylation. Number 6, Friedel-Crafts acylation. These are the reaction. These reaction, if they are carried out on a normal benzene, they gives only one type of the product, only single product is obtained. But if the benzene is if benzene containing any substituent, suppose as a monosubstituted benzene, and then these type of the reaction again carrying out on the substituted benzene, then there is a mixture of the products are obtained. There we are getting ortho product, meta product, and the para products are there. Suppose as a why some of the monosubstituted benzene gives the para product major, some of them gives the meta product major, some of them gives as ortho product major. Why this happen? That is nothing but is called as orientation. And the reactivity, if you consider some of the compound, aromatic compounds are there, like as a, let us see simple benzene. Imagine that simple benzene. Then second one is a, suppose as a toluene. We know that alkyl group attached to that benzene ring or the nitrobenzene. Suppose these are 3 aromatic compounds are there, and out of that 3 aromatic compound, if you talk about the reactivity, which compound, whether the first benzene is more reactive or toluene is more reactive or nitrobenzene is more reactive, how do you decide their act reactivity order. So that is called as a reactive. Which one of them? Because among these three, one must be as a more reactive toward the and as we know that aromatic compound has a special characteristic. They undergoes electrophilic substitution reaction. In a special condition, they undergoes only as a nucleophilic substitution reaction, and they do not undergo addition reaction. That is also we have learned. Why they do not undergo as addition reaction? Because if they undergo as addition reaction, they lost its aromaticity, and therefore they do not show as addition reaction similar to as a alkene, even though they containing as a carbon-carbon double bonds are there, and they are the unsaturated, but they are not showing the characteristic property similar to as alkene. Don't, because addition, the alkene, they undergoes as addition reaction. In an addition reaction, the atom or reagent whatever we are adding, they get consumed in the across the olefin or the carbon-carbon double bond, and the resulting product is obtained as a single product. So that type of the reaction is called as addition reaction. But these, even though containing as an unsaturated compound, they do not undergo as addition reaction. Instead, they undergo as a electrophilic substitution reaction more readily. That we already learned that, and therefore this point is a very important. Whatever you have predicted the product about the aromatic compound, just by knowing your teacher are saying, suppose as a benzene treat with a nitrating mixture, resulting compound is a nitrobenzene, you are fixed there. But why we are getting as only as a nitrobenzene? So with the mechanism we are going to learn. Or suppose your starting compound is a toluene, and you are carrying out the reaction under the same reagent, that is a nitrating mixture, and then you are getting as a two products are there, or more than two products are there. There is always competition about the formation of that product. One of them is a formation of the product is a major in quantity, another is a minor in quantity. Which of them is a major in quantity and which of them is a minor in quantity? How do you know? For that purpose, there is a orientation. If you know the orientation while studying this, we are going to get the answer of those questions here today right now. Why? Because that effect of substituent groups means what type of the effect they are having. Depending upon that effect, that the orientation is decided. And as we know that, let us look at here. Suppose as a benzene ring is there. Let us see here. I am trying to draw this is a benzene ring, and as we know that benzene having as a molecular formula CH-6, right? And now all the 6 hydrogen atom of the benzene are identical, and therefore when they undergoes as we know that they undergoes as a electrophilic substitution reaction, and they produce the product nitration reaction, sulfonation reaction, halogenation reaction, Friedel-Crafts acylation reaction, Friedel-Crafts alkylation reaction, diazocoupling reaction. That is in this chapter we are learning. Now effect of substituent on groups. Now suppose is a benzene is there. If you carried out as a nitration, suppose as a NO2 plus is treated, you are going to get the product is this one NO2. Suppose you have if you treat with SO3 that sulfur trioxide, that is fuming H2SO4 sulfonation reaction, you are going to get the product SO3H, that is nitrobenzene. Here is a sulfonic acid, and now if you treat this compound with RX in presence of AlX3, you are going to get the product is this one, right? There is here is a R is introduced here. This is a Friedel-Crafts alkylation. Here we are getting only as a one product. But why we are getting as a one product? Because all the hydrogen atom on a benzene ring having the chemical environment around it is identical. They are chemically equivalent, and therefore resulting compound we are getting as a only one. So that is a monosubstituted. And when we are in general, if you add here as a electrophile, right, here if you add as a electrophile, because they are readily undergoes as electrophilic substitution reaction, and we are going to get the product is this one, that is one of, just like as a nitration, sulfonation, halogenation, Friedel-Crafts alkylation, these are the things. Okay, only monosubstituted benzene we are getting. Suppose you have already as a monosubstituted benzene over there, right? Let us see, here is a Y group is there. Let us assume this is called as a monosubstituted benzene. Monosubstituted benzene, this one, right? And when the monosubstituted benzenes are there, the all whatever remaining, monosubstituted means what? One of the hydrogen atom from the benzene get replaced by any group. Let us see here, just as a Y group is here. And now when you are carrying out the electrophilic substitution reaction, you may get the product. Sometime you are going to get the, how many products are possible? Here is a Y is there, right? This is, and now where the electrophilic is going to attack, you can attach this electrophile either, because look at here, there are these two positions. These two positions are termed as O. O means what? Ortho. Remember, these are two identical. This is a, if you put here is a, so if you cut this molecule, or if you put as a mirror, these two positions are identical. They are adjacent to that Y group, and that position are termed as a ortho position. These two hydrogen atom are ortho hydrogen atom. Now if you look at these hydrogen atom and these hydrogen atom, or these two positions, these two positions are also identical. This, and they are termed as a meta position, right? This is known as a meta position. And exactly opposite to this, only one of the hydrogen atom or this position is termed as a para position, right? There is a ortho, meta and para position. These are the three positions with respect to that R group. With respect to that Y group, we don't know the Y group, and Y group is a, suppose, let us see here, Y group we are treating as a electrophile. Electrophile may attach at this position, you are going to get as a ortho product, right? Ortho. And if it is attached at this position, why I am putting as a fix at this position, and here I am going to get the electrophile is going to attach at meta position. This is called as a meta product, right? This is ortho product, meta product. And another one, again possibility is there. This Y, again you are going to get, electrophile is going to replace the para hydrogen atom, and you are going to get as a para product. So this is a para product. So these are the three products are possible if the Y, this substituent is a Y. We don't know the nature of that. Remember, on a benzene only two type of the groups are present. If Y is equal to, it may be as, if it is, remember, if Y is a electron withdrawing group, you can call, or electron donating group. Electron donating group. Suppose the nature of Y is a, what we can call it as a electron donating group, then and then this we are talking about the effect of the substituent group. Means suppose your substituent is a electron donating group, like any R group or 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 OH or NH2 etc. These type of the groups are there. They having a ability to donate the electron to the benzene ring, and this type of the group is called as a electron donating group. Electron donating group means they are donating the electron to the benzene ring. Benzene, as we know that it is already electron rich in species, again that group also donating as a electron, and therefore that benzene becomes as a richer and richer, means they are more electronegative in nature. If that is there, they always gives ortho and para product, means their orientation are ortho and para. Remember, suppose as a benzene ring containing as a this kind of the groups are there. Suppose as a alkyl group, electron donating group, or OH group, or OR group, or NH2 group. If electron donating groups are present on the benzene ring, they gives the ortho and para product. They are giving as a this type of the product only. Suppose this product, and why they give only those products, that we will see shortly. And if suppose as a y is equal to electron withdrawing group. If Y is the electron withdrawing group, like as a nitro group NO2, or COOET ester, COOH, carboxylic acid, or C double bond OH aldehyde group, or what we can call it as a cyanide group. These are the electron withdrawing group. If the nature of Y is the electron withdrawing group, electron withdrawing group means what? The atom or group of atom removes the electron density from the benzene ring. When they removing the electron density from the benzene ring itself acting as a electron deficient in nature, and therefore whenever you are adding as a reagent, and as we know that aromatic compound undergoes electrophilic substitution reaction, if such type of the groups are present on the benzene ring, they gives only as a meta product, means they are the meta directing. You can call it as a meta direct. If electron donating groups are present, they are the ortho and para director. Director means what? They are directing what kind of the product they are producing, that is depending upon the electron donating group. If electron withdrawing groups are present, that group, the group which is present on the benzene ring directed what kind of the product they are going to produce. They are always producing, or always end with they are the meta director. Meta director means the product is obtained is a meta product. Always remember, if the benzene ring containing as a electron withdrawing group, they produce the meta product, or they give the meta product, or they form the meta product. Why they form as a meta product only? Why not ortho and the para product? That we will see here. Why they are producing? The reason we are going to find out here. And let me just, before that, orientation we are talking, we are getting as a ortho, para, and the meta products are there. That is called as a orientation. Just now we have seen, right? So now let us talk about suppose we have this type of the reactivity. Just now we have seen their orientation we are getting here. Orientation we are getting as ortho, meta, and the para product, depending upon the nature of the substituent. Nature of the substituent, what type of the substituent present on the benzene ring, according to that we are going to get as a product. And when we talking about the reactivity again depending upon the what type of the groups are present. Let us consider, suppose as a reactivity of these three compounds are there. Let me draw here some of the compound. This is a benzene, as we know that, right? Benzene. And let me draw one of the compound here. Let us see here is a, as we know that what is this? This is a nitrobenzene, and this nitrobenzene can be obtained when the benzene treated with nitrating mixture under a suitable reaction condition, producing as a nitrobenzene. And now I have another compound. All are the aromatic compound. These are, suppose let us see here, I am writing as a toluene over there, right? These are the three compounds are there. As we know that this is a simple benzene, this is the toluene, means it is a monosubstituted benzene, and monosubstituted benzene, nature of this group, this methyl group is act as a electron donating group. This is a electron donating group, right? An electron donating group, and this one nitro group, it is a electron withdrawing group. And when electron withdrawing groups are there, they withdraw the electron from the benzene moiety, and this electron donating group means they donate the electron to the benzene ring and they withdraw the electron. The arrow should be like this, and they are giving means arrow pointing toward the benzene ring. That type of the things are happening here. Now when we are talking about the reactivity about these three compound, number 1 A, B and C. What do you think? Which compound is the most reactive one and why? You look at here the whether if you compare between these two, one is a nitrobenzene, another one is a benzene. Among these two, which one is a more reactive toward the electrophilic substitution reaction I am talking about? Because the aromatic compound undergoes the electrophilic substitution reaction readily, means here we are going to introduce as a electrophilic substitution reaction. So reactivity also we are talking about the electrophilic substitution reaction. If you compare between these two, which one is a more reactive, whether the benzene is more reactive or nitrobenzene is more reactive? Here remember, nitrobenzene is a less reactive as compared to as a benzene, means benzene is a more reactive than the nitrobenzene, because here what is happening, nitrobenzene is electron withdrawing group, the nucleophilicity of that benzene is decreases. Once the nucleophilicity of the benzene goes on decreasing, the reactivity toward the electrophilic substitution reaction goes on decreasing, and therefore benzene is a more reactive than the nitrobenzene. If you compare between these two now, there is a exactly opposite. Here the toluene, as we know that benzene is a nucleophilic in nature. This alkyl group also providing electron, means it becomes as electron rich, electron richer, and therefore it is a more reactive toward the electrophilic substitution reaction, means toluene is a more reactive among these three compounds, right? Understood this one? Now let us why we are getting as a ortho and para product if suppose electron withdrawing groups are present on the benzene ring. Now let us look at, suppose you have this type of the compounds are there. Now let us see, suppose you have what we can call it as a next point, we are going to see the sulfonation of benzene and toluene. 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 For example, suppose we have here, let us we are talking about the effect of substituent group orientation and the reactivity. You might have learned this one, but why suppose as a let us see, suppose you have this group. Now let us see here this group, right? And now suppose here let me give here what we can call it as electron donating group, like as a OR, let us see OCS3. Suppose is anisole is there, right? And anisole, as we know that this is a structure of anisole, and this anisole if treated with suppose the nitration is carried out here. Let us see here concentrated HNO3 in presence of concentrated H2SO4. You are going to get the product or this one. One product is this one OCS3. One you are going to get here NO2 group. Another product you are going to get, the another product will be this one OCS3, and at this point that is this one. This is called as orthonitroanisole. This is orthonitroanisole, and this one is called as a paranitroanisole. Why? And now when the two products are formed, as we know that there is a competition between these two products. One is formed in a major and one is formed in a minor. Which one is a major and which one is a minor? What do you think? Here you are going to get this one is a minor, whereas you will get this one is a major one. Why this one is a major and this one is a minor? Because the question arises, why one we are getting as this one is a minor and that one is a major. So if this is a major, why this one is a major, and it is a minor, why this one is a minor? Look at here, this is a bulky group, this is also as a bulky group, and both the bulky group, if they are nearer to each other, there is a steric hindrance, or what we can call it as a steric interaction, and due to that steric interaction, because they are not having a sufficient space to accommodate that two group, and they are trying to push each other, they are trying to repel each other, and when they are repelling each other, due to the steric interaction or steric hindrance, there is a internal energy increases, and as we know that a general guideline, as the internal energy goes on increasing, and then the stability of that compound goes on decreasing. Similarly, but if you look at here, the group which is present O-methoxy and nitro group, they are well separated from each other. There is no steric interaction, and therefore this one is obtained as a major, and this one is obtained as a minor. This is a major and this is a minor. Why? Because here is a steric interaction or steric hindrance is there. Due to this reason, the internal energy decreases, internal energy is increases, and that's why the stability of that compound is less. It is formed in a less percentage, whereas this is formed in a more percentage. Why this we are getting as a ortho and the para, why not the meta? That is the main question arises here. Why? The answer is here. If you know the resonating structure, then and then you can justify, you can get the answer why we are getting as this one is a ortho and the para product. Those are knowing the concept of resonance, how to draw the resonating structure. You are learning from your 11th standard, 12th standard, T.Y.B.Sc, S.Y.B.Sc. But those are knowing the concept of resonating structure, they can predict the product very, very correctly or very perfectly, because the answer is involved in the resonance structure. Now, if you draw the resonating structure of this compound, you know that how to draw the resonating compound. There are the certain rules are there. On the basis of that, you can draw the resonating structure. Let me draw here clearly. Now you know that the benzene has an alternative carbon-carbon double bond, the lone pair which is present on the nitrogen atom. Now what is happening here? The lone pair, this is the electron donating group, it donating the lone pair, forming the bond between this carbon atom and this oxygen atom, and at the same time what is happening? This double bond concentrate the electron density at this corner point or at this junction. Remember, show the arrow perfectly. And now what are the changes I made? I formed the double bond here and CH3. Now look at oxygen has a 3 bond, one with methyl group and 2 with this double bond, and therefore I am putting positive charge on the oxygen atom. And now the negative charge at this corner point. And now remember, this carbon atom and this carbon atom, they remains as it is, means they are intact. I am writing they are as it is. And now another resonating structure. Remember how to show the arrow. If you pay the attention carefully, you can able to draw the resonating structure very perfectly or cleanly. Look at here, this negative charge, I am putting this negative charge exactly on that corner point, not on either side or that side. Remember, because everything in organic compound must be defined, or what we can call it as a clear cut, you have to show. Now this negative charge coming down, forming as a double bond between these two carbon atoms. Look at these two corner is nothing but as a, there is a carbon atom. Remember, and now forming as a double bond, and at the same time this double bond concentrate the electron density at this corner point, and you are going to get the next resonating structure. What are the changes I made here? Forming as a double bond and negative charge coming on that corner point. Now look at the what are the thing remains as it is. This double bond is as it is. Then this double bond with that oxygen atom as it is, and then positive charge you keep as it is, right? And now another resonating structure. Now what is happening? Look at again carefully. This negative charge moving, forming as a bond between this carbon atom and this carbon atom. I am showing that arrow resting exactly middle of this bond, and therefore now at the same time this double bond concentrate the electron density at this corner point. Again I am showing, pointing exactly at this corner point, so arrow resting on that corner point, and then draw the next resonating structure. What are the changes I made? I form the double bond here, then negative charge here. Now this double bond OCS3 positive charge remains as it is. This double bond, it is also as it is, right? Now draw the another resonating. Now what is happening? This negative charge coming and forming as a double bond between these two carbon atom. At the same time this double bond neutralizing this positive charge, and we are going to get the final structure. What are the changes I made? I made double bond here, then OCS3 known pair present on that oxygen, and now look at this double bond, they are as it is. The double bond is as it is, and after traveling that lone pair coming on its original position, resonating structure, if you remember the definition or the statement of the resonance effect, the redistribution of electron operating in unsaturated system via pi bond is known as a resonance effect. Therefore this lone pair get redistributed, means this double bond is not localized, they are redistributed, means they after redistribution they are coming on its original position, and that type of the structure are known as resonance structure or canonical form. Now look at here, this is the structure number first, this will be the structure number second, this will be the structure number third, this will be the structure number 4, and this will be the structure number 5. There are 5 structures are there. Now see the structure number first and structure number last carefully. What do you observe here? Here look at the double bond on the right hand side. If you look at the last structure, the double bond placing or present on the left hand side. This is the changes in structure number first and the last. Now observe carefully. Now leave that structure number first and structure number last one. Don't think about that. Now concentrate or pay the attention toward these three structure. Look at structure number second, structure number 3 and structure number 4. If you see the structure number second and structure number 4 carefully, what do you see? On the right hand side there is a negative charge, on a left hand side at ortho position, because as we know that these two positions are identical, and these two position means at a ortho position there will be a negative charge. And when you are adding the electrophile, and here electrophile is NO2 plus, means E plus are there, and now at ortho position is a negative charge and positive that is attacking at ortho position. Understood this? Why we are predicting as a ortho product? Got the answer here. Look at here, why we are getting as a ortho product? Because here is at ortho position there will be a negative charge, and this aromatic compound they undergoes as electrophilic substitution reaction. And now look at on the left at this structure number 3 carefully. What do you observe here? At structure number 3 at para position there is a negative charge. When the negative charge is there, and therefore the electrophile attacking preferentially at the para position, and therefore if the electron donating group present on the benzene ring, they are the ortho and para director. Ortho and para director, it means that we are always getting as a ortho and para product if the monosubstituted benzene having the electron donating group. Understood? If electron donating groups are present, they are always giving as a ortho and the para product. That's it. And if ortho and the para, there is a competition between ortho and para, which one is getting as a major? Para is always a major over the ortho. And why we are getting as a ortho product is a minor? When that two bulky group nearer to each other, they create a lot of steric interaction, and due to that internal energy increases. Once the internal energy increases, the stability of that molecule goes on decreasing, and therefore this one is more reactive compared to as this one. Now let us look at as another example where we are talking about the orientation of the effect of substituent on a group, means orientation and the reactivity. Now let us look at as one example over here. Let us see, suppose I have this structure. Now this suppose as a nitrobenzene, C double bond O, here is a positive charge, here must be as a negative charge, right? Now this is a nitrobenzene. When that nitrobenzene again further treated with concentrated HNO3 and the concentrated H2SO4, this is, we know that it is a nitroting mixture. This reaction is known as a nitration reaction, and the product we are getting as a nitrobenzene. But here we are taking as a substituted substituted benzene, and that nitro group is already present, and we are carrying out again as a nitration on it. We are getting as a two product. Let us see here what are the product you are going to get. You are going to get as only one product. NO2 groups are there, and if here for sake of convenience you can write over here, here is a this is a nitrobenzene, again further treated with the nitrating mixture, we are getting only as a one product, only as a meta product. This is a meta product we are getting. Why we are getting as a meta product? That is a major question over here, and the answer is here. Those are knowing the concept of resonating structure, they will find the answer over there. Now look at here, answer is over here, and as we know that, again draw the resonating structure. C double bond O, here is a minus charge. Now positive charge on the nitrogen atom. Why I am putting positive charge on the nitrogen atom? As usual, nitrogen atom carry as a 3 bond, but here look at, there are the 4 bonds are there, 1 2 3 and 4, therefore positive charge on it. Now see the resonating structure. In a previous case we know that this nitro group, what is it is? It is a electron withdrawing group. Electron withdrawing group means what? It withdrawing the electron density from this benzene ring. Now this benzene is a nucleophilic in nature, carbon-carbon double bonds are there. Now this double bond now shifted from here to here, and then this double bond concentrate the electron density on this oxygen atom, and as we know that oxygen atom is more electronegative than the nitrogen atom, and therefore we are getting this type of the product. Here we are getting carbon nitrogen double bond O minus, and here O minus as it is. Still nitrogen atom has a 4 bond, and therefore I am putting positive charge over there, and now the rest of the thing remains as it is. This double bond remains as it is, this double bond also as it is. Now look at carefully, when I am shifting this double bond from here to here, so what is happening? What type of the charge present on this corner point? What do you think? Yes, there is a positive charge present on that, because this nitro group is electron withdrawing group, it withdrawing the electron, therefore this nucleus, benzene nucleus finding is a electron deficient in nature, and therefore positive charge comes on that nitrogen, comes on that carbon atom. Now look at there, most of the students get confused here, showing as arrow, because in a electron donating group, how we are showing in a previous case, if you remember here, CH3 donating electron, so the double bond forming here, and this double bond concentrate the electron density at this corner point, and therefore there is a negative charge I am putting over there, double bond O, CH3 positive charge. Look at here how the arrow I am showing while writing as a resonating structure. Here you can clearly see this difference. When this electron withdrawing, it withdraw the electron, and that's why positive charge. Now the next, what is going to happen in a negative? I am showing this negative just like as a water. Water has a tendency to flow from higher level to as a lower level. Similarly, this negative charge coming down, forming as a double bond over there, and negative charge over there, and you are getting here the product is like the double bond, negative charge here, this double bond remains as it is, O, CH3 positive. We already seen in a previous case, but those are not getting that point. I am trying to explain here while showing as a arrow between electron donating group and electron withdrawing group. There you remember. Now here shifting here. Now this double bond, now look at carefully, this double bond is nothing but as a number of electron, and this double bond shifted from here to here, neutralizing this positive charge. And now what I am going to get here? Here, what are the changes I made? Look at here. Now when double bond shifted from here to here, positive charge comes on that corner point, there will be a double bond, and this double bond remains as it is, other thing remains as it is, O minus, then O minus positive charge as it is. Now look at here again, those are the students. Suppose this is exactly in the middle, some of the students showing again this double bond. Don't do that one. If you start from this anti-clockwise manner, so remember that one, this double bond shifted, not this double bond, because we already shifted. We are starting from this positive charge is moving clockwise manner, so keep the trend as it is. Now this double bond shifted from here to here, so that we are going to get the next structure will be this one. Now what are the changes I made? Double bond here, positive charge at this corner point, this double bond O minus positive charge here, and this double bond remains as it is over here. Now when this is happening, now what is going to happen? Remember, here also most of the students get confused. Now this negative charge coming back, forming as a double bond between this nitrogen and oxygen. This double bond shifted from here to here, forming as a double bond over there, and you are going to get finally this one double bond here, nitrogen, double bond O, positive charge still remains on it, this double bond as it is, and this double bond also as it is. Now look at the number of structure. First, this is the second, this is the third, this will be the fourth, and this will be the fifth. There are the 5 structure we are getting, and look at the structure number 5. First and 5, they are identical, there is no change, but in this case a double bond on the right hand side, in this case double bond on the left hand side. Okay, leave that 2 structures. Now concentrate on structure number second, third and fourth. What do you see? Look at in structure number second, at ortho position there is a positive charge. At third, if you look at here, again at para position there is a positive charge, and here look at again ortho position there is a positive charge. And why we are getting the only one product which is a meta product? Because at ortho position there is a positive charge. When this is happening, there is electrophile, means NO2 plus is there, and NO2 plus and plus plus there is a strong repulsion, means there at ortho position you are not getting any substituent attached, only the possibility remains there, they are forcefully attacking at meta position only, and that is the reason why